Okay, welcome to the next video of Unit 5. So right now we're going to be continuing on, let me just change up some colors here. We're going to be continuing on with Unit 5. And Unit 5 was thermochemistry. So if you're just joining, of course, make sure to watch the previous videos in this series. I believe this is like the 5th video or something. And we've already covered a little bit of heat and the equation mc delta T. We've covered molar enthalpy and how to do the calculations for both of these. We've covered a state function versus a path function. So we covered a state function versus a path function, heat, enthalpy, and that's about it so far. So today what we're going to be covering, today the new part is going to be the enthalpy change, enthalpy of formation. Enthalpy of formation. So what the enthalpy of formation is sorry, I just got to reposition a little bit. The enthalpy change of formation, it's basically, well, I'll write down the equation first, and then we're going to discuss the different parts of it. So delta H naught of the reaction equals the sum of the delta HF of the products minus the sum of the delta HF naught of the reactants. So this is a little bit different. This is going to be a little bit different than previously, right? In IGCSE, we would have done delta H equals the bond energy, the sum, sorry, that's a bad sum sign, the sum of the bond energy of the reactants minus the sum of the bond energy of the products. Because, right, this would just show us that if the products had stronger bonds, means that they're more stable. So this one would be less stable, which means that our delta H would be negative if our products have stronger bonds, and our delta H would be positive if our reactants had stronger bonds. But right now we're going to be discussing what the enthalpy of formation is. So let's define what these are. So we got delta H naught reaction. So that means is that's the total enthalpy change of the reaction. So that's typically an R here, delta HR or delta H reaction. Delta HF naught is the enthalpy change of formation. So in order to define what the enthalpy change of formation is, this is going to be included, let me just do a side note right here, included in your section 12 of your data booklet, which of course is your most important booklet for paper 2 and paper 3. Section 12 of the data booklet. And what this enthalpy change of formation is, this is going to be the fun part. So basically, let's try to think of an example I can do. I might need to do the example in the next video, but I will help you solve through these, don't worry. But basically, the delta H of formation naught. So what this means, let's break this down into different parts. So we've got delta H, F, and naught. So what the naught sign means, it means under standard conditions, which means at 25 degrees Celsius and at 100 kilopascals. So under standard conditions, the delta is the change. So delta H is negative if it's exo, positive if it's endo, and the number is basically how much energy is released or how much energy is absorbed. How much energy released or absorbed. And then the F is that we're talking about formation, because in the next, or one of the two videos from now, you're going to see the enthalpy change of combustion, which is written delta H naught, meaning it's at standard conditions, enthalpy change, and C. So combustion instead of formation. What this means, let's talk about the implications of what this is. So delta heat of formation. So what this does, if we do have some sort of reaction taking place, right? So let's take CH4 plus Cl2 reacts to form CH3Cl plus HCl. So let's look at this reaction. So another way of calculating, we said that enthalpy is a state function. So it doesn't matter how we get to these products. We can still calculate, or how better to say this, we can either calculate it the old way, which was up here. But the thing is that we need to use a standard table. We need to know the bond energy of the reactants, the bond energy of the products. So no matter what, we have to use a table in this case. But here we also have to use a table because we're going to break this up into multiple steps. We've got CH4. What our delta HF under standard conditions mean is it means what is the enthalpy change of forming methane. So if I were to write down this reaction, we'd have carbon plus hydrogen reacts to form CH4. So let's just double this up so that we're balanced. And if you look in your data booklet, what you're going to see is the enthalpy of formation. Oh, that's enthalpy of combustion. Sorry, I just got to rotate this. Enthalpy of formation right here. So I just need to rotate this a little bit. There we go. So the enthalpy of formation of methane, delta HF of methane, negative 74 kilojoules per mole. So you've got this is negative 74 kilojoules per mole. So when we form methane out of its products, out of combusting carbon with hydrogen, we release 74 kilojoules per mole of energy. So that's our delta HF of CH4. And now we do Cl2. So what you're going to learn is that, or what I'm going to tell you actually right now, is that for pure substances, so this is going to be for elements, not pure substances, because CO2 is a pure substance. If we just got a container of only CO2 with nothing else in it, that's a pure substance. So elements, the delta H of formation is 0. So the delta H of formation is equal to 0. Because it's an element, we haven't had to react anything to form that, because that is what it's like at standard state. That is its standard state. Chlorine likes to exist as chlorine gas, and CH4 is a gas, but carbon likes to exist as a solid, and hydrogen likes to exist as a gas, and CH4 exists as a gas. So basically, this is its standard state. If we had a room full of chlorine, it would all be existing as Cl2 in gas phase. But then we can look up, maybe we've got it here, otherwise I'll have to look it up. But so now if we wanted to, start the equation, minus delta F of the reactants. So we need delta H naught of the reaction is equal to the sum of delta HF naught of the products minus basically this, minus 74 kilojoules per mole. So we've got one of them, and then our second one is 0. Or not 0, yeah. The second one, there's no enthalpy of formation, so we don't take into account. Otherwise, we multiply that by 0, we have 0. So okay, let's hope this is in the table. So the delta H of formation of CH3Cl of a chloromethane and hydrochloric acid. So let's see. Chloromethane right here, negative 82 kilojoules per mole. So we've got this right here is negative 82 kilojoules per mole. And let's see if HCl is in here too. Maybe we'll be lucky. HCl, negative 92.3. So that's negative 92.3 kilojoules per mole. So if we did this, if we calculated our delta H of reaction, so the way to think about this, let me just erase this over here, and we're going to go to it. So since we said that enthalpy is a state function, it doesn't matter how we arrive at the final product. It just matters that basically they all add up. So CH3Cl, how we would form this, we'd have to react carbon in its standard state, which is a solid, plus hydrogen in its standard state, which is a gas, plus chlorine in its standard state, which is a gas, and we have to form CH3Cl. So that if we were to balance that, we got to double that, we have to triple that, double this, and this overall reaction, if we were just to take, perfect conditions in order to react all of these together, we would find out that negative 82 kilojoules per mole is released. So you can see that this is it's not a burning reaction because we're not reacting with oxygen, but it's a reduction reaction. We're reducing the carbon, but we're oxidizing the carbon at the exact same time because we're adding the chlorine to it. So you can see that, we are still adding compounds together. We are forming bonds, and forming bonds is exothermic. So we've formed lots of bonds and we've released energy. So if we were to do this calculation, now let's see the sum of the delta H of the products, which you need to use this section in your data booklet. You need to use it. So let's do this calculation. So it's negative 82 kilojoules per mole plus negative 92 point, let me see, HCl was negative 92.3 kilojoules per mole, and then minus a negative number. Minus means plus 74 kilojoules per mole. So if we were to find out the final value, the final product, we'd say delta H R naught of this reaction is equal to, let me just get my calculator open here. So is equal to, we do 82 plus 92.3 is equal to negative 174.3, negative 174.3 plus 74. So this is easy math, quick math. 2 plus 2 is 4. So minus 100.3 kilojoules per mole for this reaction. And you can see we haven't used the bond strengths. Well, what we've done is we've said that enthalpy, enthalpy doesn't care how we get there. So we can say, okay, this, forming this releases this much energy. Forming this releases no energy because it's in standard state. figure out the energy to form this, figure out the energy to form this, and then we could just add all of those energies together, because it doesn't really matter, right? It's the fact that chlorine is here, we can do it in the old way and calculate the bond strength of carbon to hydrogen, calculate the bond strength of chlorine, calculate the bond strength. So we can do all of that, or we can use the heats of formation, the standard heats of formation. So okay, so that's our example for how to solve these questions. Basically take the reaction, use your data booklet to find out the enthalpies of formation, and do not forget your equation. That's delta H formation of the product minus delta H formation of the reactant. So do not forget this equation. This is so put a bunch of stars beside it, put all the glitter you've got in the house next to it. We need to remember that equation. So yeah, so the last one, last thing I want to kind of reiterate here, just in case it comes up for you guys. Remember to use your data booklet. That never ceases to come in handy, right? If you're in paper 2 and you think, okay, this question doesn't give me enough information, crack open your data booklet. It's safer checking that. So I want to cover one last thing, what this means. So right, we said it was the standard enthalpy change at standard conditions. So at 25 degrees Celsius, which if we convert it to Kelvin is 298.15 Kelvin, at 100 kilopascals pressure. And also, so this is the important note, so all species are in their standard states. So that's the state that they exist at 25 degrees Celsius and 100 kilopascals. So right, if we were looking at a molecule, let's just say ethanoic acid. If we were looking at this molecule right here, right, to calculate the standard enthalpy of formation, let me just erase this example off the screen. So to calculate the standard enthalpy of formation, all you have to do is you take all of the elements that compose it. So we've got, there, pink is good, carbon, we've got oxygen, we've got hydrogen. You put them into their elemental states like I have right here, and you add them together. So you do carbon plus oxygen plus H2 forms ethanoic acid. And you put them in their standard states. So you know, at room temperature, carbon exists as it's a solid, oxygen exists as a gas, hydrogen exists as a gas, and ethanoic acid exists as a liquid. So basically, these are their standard states, how they exist at room temperature. So hopefully this video made sense. It seems to make sense to me. If not, we have that meeting this week through Google Meets, and we can finally discuss that. So just remember, state function means you don't care about how you got there. Path function means you care about how you got there. And our delta H of reaction is the sum of the heats of formation of the products minus the sum of the heats of formation of the reactants. I have also, in Google Classroom, posted a video to, and this is an amazing website, Khan Academy, on videos that they talk about enthalpy. So I highly recommend supplementing my videos with these videos for all of Unit 5. Because Unit 5 is a difficult unit, lots of calculations involved. Use as many resources as you possibly can. So okay, thank you very much. I'll see you next time.